Hey guys, this is Malinki. Welcome back to my channel Voice of Malinki. Today we will talk about native polyacrylamide gel electrophoresis. And if you are new in my channel, please subscribe my channel. And if you like my video, please do like, comment and share my video. So let's talk about native page. So native page is a technique that is used to separate protein molecules based on their net charge, their size and shape of the native structure. So shape of native structure. That means based on their native structure means based on their original structure, right? Original structure and shape. Here we use acrylamide gel. So acrylamide polymerize to become polyacrylamide gel. This polyacrylamide or this polymerized acrylamide, it forms a mesh-like structure. So like this. Mesh-like structure like this. So it is done by polyacrylamide, right? And this mesh-like structure is suitable for protein separation. Now protein samples are loaded into wells. So here you can see, suppose this is the gel. This is the gel and here we have some wells. So in this picture here you can see that these are some wells, right? So protein samples are loaded into these wells at one end of the polyacrylamide gel. This is the polyacrylamide gel. And this gel is placed in the electrophoresis chamber that we can see. This is the chamber. This is the electrophoresis chamber and that is connected to the power. This electrophoresis chamber is connected to the power. And the electrophoresis chamber consists of a negative charge at one end, that is cathode. So it has, in this end it has cathode that is negative charge and at this end it has anode that is positive charge, right? Now when the electric current is applied, protein molecules are pulled down through the gel like this. Protein molecules are pulled down in this way. Now what is the principle of this native gel electrophoresis? So basically proteins are composed of amino acids, that we know, right? Proteins are composed of amino acids, right? Now these individual amino acids may carry positive or negative charge or no charge at all. Therefore, because of this individual charge of each and every amino acid, the whole protein molecule has an overall net charge, right? So the whole protein molecule also has an overall net charge because its each component, that is the each and every amino acid, contains either positive charge or negative charge or no charge at all, right? But one thing that the net charge of a protein is also dependent on the pH of the surrounding medium. So, net charge of protein is dependent on pH of surrounding medium. Therefore, at a particular pH of the medium, the net charge of a protein could be positive, negative or neutral. Now, in native gel electrophoresis, what we do, the pH of the buffer is set such that all proteins at that pH carry a net negative charge. So, in native gel buffer, all proteins are negatively charged due to the pH of this buffer, right? Therefore, all the proteins migrate to the positively charged electrode, that is anode. So, we have seen in the last picture that this is anode, and all the proteins migrate toward the anode because proteins are negatively charged. So, they will migrate toward the positively charged anode. Now, the higher the negative charge a protein molecule carries, the faster a protein will tend to migrate. So, higher negative charge, higher will be the migration speed of the protein, right? Now, at the same time, the frictional force of the gel matrix regulates the movement of proteins according to their size and shape, because the gel will have some frictional force, and that force makes some hindrance. Now, small proteins face a small frictional force, right, compared to the large proteins. Therefore, a small protein moves faster in the gel compared to the large proteins, because due to the friction, large proteins get entangled in the mesh. So, suppose this is the mesh, and the large proteins, suppose this is the large protein. So, large proteins are entangled in the mesh because of the frictional force, or because of the friction of this matrix, right? Now, small proteins receive less resistance, right? So, if this is the small protein, it will get less resistance. Next, that globular proteins are compact. Suppose this is a globular protein like that. So, this protein is very much compact, right? Therefore, they migrate faster compared to linear proteins. Suppose this is the linear protein. So, the globular protein is compact and it will move faster compared to the linear protein. So, what we have seen here, that large negative charge density, smaller size and globular shape of protein mediate faster migration compared to less negative charge density, large size and linear shape. Now, what is the advantage of using native gel over SDS? Okay, so because we use both native and SDS gel electrophoresis for protein separation, right? So why and when we will use native page? So in case of SDS page, we use a denaturant. In case of SDS page, we use a denaturant, that is sodium dodecyl sulfate or SDS. This SDS denatures our protein samples. But in native page, we are not using any kind of denaturant. No denaturant here. Therefore, all proteins retain their quaternary structures. So, structures are intact. So, all proteins retain their intact structures or their quaternary structures here. That's why it is called non-denaturing gel electrophoresis. This is also called non-denaturing gel electrophoresis. In fact, protein function also remains unchanged after the separation process. So, protein function remains unchanged after the separation process. So, suppose you are working with an enzyme. So, it will retain its catalytic activity even after the separation. Therefore, it is possible to recover proteins in their native state after the separation. That's why it is called native page electrophoresis. This is the advantage of native gel over SDS.